until now we have covered the rectifiers and then DC to DC, and today we will cover DC to AC inverters. So this type of inverter is used to convert the DC current into an AC. So this one also, there is lots of application when you talk about renewable energy for both. For example, when you talk about wind or you want like to talk about solar, you need those, because this inverter DC to AC inverter will, including filter you can add, it can be 3-phase, by the way, it can be single phase, and this one it can be connected to a grid, or it can be connected as a standalone system. So that means if I have a DC which is coming from boost converter or from whatever you can call it from the side, you can get this DC to an AC, and this AC at this level here or at this place is distorted, and then again a filter used to filter the harmonics components or the noise, and then you will get the fundamental components, which is a sinusoidal waveform with the required standard like 50 Hertz or 60 Hertz in some countries. And the voltage level here should be also controlled depending on your system. If your system is a standalone, that means you need to make like a voltage control system to control the firing angle to that one using voltage control, so that you can control the voltage. In addition to the frequency, you need to control the frequency and the voltage. This is one system. For the grid connected system, definitely when you have a grid, this is, if I assume this one is standalone, if it is connected to a grid, okay, through filter and then filter here, and then to the DC to DC to AC inverter, and here DC input, it could be from solar, it could be from wind, which is type 4 wind, type 4 of wind turbines. So if you look at here in this system, the frequency and the voltage are controlled by the grid. Therefore, in this case, my controller to that one can be established by just controlling the power, which is the power which should be injected from the DC side to the AC side, and also it could be reactive power. No, mostly until now they just use it to control the repower, and they operate it around unity power factor. It could be 0.95 lead lag, but for the reactive power until now, rarely it is used to inject the power from renewable energy sources. So this is the difference between those. So here I need to control those because this voltage and frequency are decided or desired by the grid itself. However, in standalone, for example, if you need to make this a system for your home, you need to control the frequency and the voltage, which is standalone or isolated system. Is it clear? So let's go through this one. For today, we will talk about this DC to AC inverters, and I will cover an application which done by your colleagues in final year project to show you how they did that project. So this is the inverter which is made by your colleague last year, and they make the circuit, and this circuit can operate like inverter, DC to AC inverter. And I think you know those guys, right? You have seen them last year. So when we talk about phase inverter, we will start by single phase. How we can convert this DC, which is here, to an AC in this load here. How we can do this one? Again, by controlling those switches. So for the first, you need to get an AC, right? So that means you need the current at this load to alternate. The current should go in this direction in one half cycle, and in the second half cycle it should go the opposite in order to get an AC, right? So alternating the polarity, right? Therefore, if I have a DC like this one and I turn this switch and this switch for the first half cycle, okay, and then turn this switch, which is 4 and 3, in the second half, I will get an AC. Let's try and let's. We'll waste our time just to.
What about the smart code?
I'm not sure. No, I should. I have to install the software here, right? And if I use those pins, I'm not sure it's going to be erased later or not. So I will not touch it like that. So let's do by simulation. Let's go to bsim and then simulate it there. So let me open. This is so. If we have a bridge like this one, okay. So if you can see on this bridge, we have 4 switches, right? 4 switches. 1, 2, 3, 4. That means we have 4 transistors. Okay. And this is the load, and this is the DC voltage. Now, suppose that if I would like to turn this switch, okay, if you look at this gating signal, okay, my frequency for that gating is 50 Hertz, and I'm going to turn on this one from 180 to 360, okay, which is the second half cycle, right? And the other 2 switches, which is that one and this one, if we open this, I will gonna to turn them from 0 to 180. So let's go to our main system. So this is our system, and you can show it in the slide. So if we look at our system, for example, if I send a signal from, let's take this is a period, right? So this is the time, x-axis, which is the time, and from 0, for example, we can put omega t from 0 to 2 pi, and then 2 pi. So from 0 to pi, if I operate switch 1, which is Q1 and Q2, okay, Q1 and Q2, the current will flow from this side, from here, through that switch or this transistor, and then toward the load, right? So the direction from the current here from A to B, and then will continue through this switch because it's on, right? And then come back toward the source again. So if I'm looking to that one now, the voltage, it's the direction into this direction, right? So that means, what's the voltage here? VAB. It is equal VDC, right? So you have a circuit like this, a DC source, okay, and the current passes through switch 1, which is Q1, okay, and then go to point A, and then from point B here, it go toward Q2 and come back to the source like this, right? So what's the voltage across the load or across this load box? Exactly with the DC source, right? So that means you will have a value, for example, if this one, suppose this is the value of this one, X value, so you will get that X or value like this until pi. Okay? Is it clear? Then, in the second interval from pi until 2 pi, okay, I can reverse or I can operate the other two switches. So instead of sending the signal to Q1 and Q2, I will send the signal to Q4 and Q3, right? So if I do that, and let's trace the current. If these two are off, remember, and these two are on now, right? So the current will flow from here through this path like this, and then look at that. The current goes from B toward A. So the polarity is reversed, right? So it is in the negative side instead of the opposite side. So, and then continue to the source. So you see it in the second period. This is for the first period. For the second period here, you will see that if you connect the source like this, the current will flow from the source toward Q4, and then from Q4 to point B, and then A like this. So, and it come back through Q3 and then to the source. So if you look at the polarity, are inverted, right? So VAB here, it's the negative, right? It's negative. So that definitely I will get, that means the value of VAB, it is minus V source, right? So if I have the V source, if I call this one VS, definitely here I will have VS value, and in the second half cycle I will have minus VS. So I will get that square wave, especially if we would like to connect it to if we have a large, for example, a large scale of wind or solar park, you can say, or solar system area or generation area, and you would like to convert this one to supply this one to a grid. The suitable method is to connect it through a three-phase inverter, right? So three-phase inverter, instead of having four switches like in single phase, we have now 6 switches. And nowadays you can find like those chips. This is from 4G. Okay, this is from 4G, and there is a 6 switches like those integrated inside that one, in addition to the control and input and output. So you can use like this chip, okay? And the rating of this one, if you look at the rating, it can afford 1,200 volt, and you can use it up to 100 ampere. So that means you can design an inverter on that one. So just connect your inputs and output and make inverter through this one. Nowadays, there is another code which is smart modules. One of the companies that manufacture those is Mitsubishi. So if you look at Mitsubishi, they even in one chip like those, they generate inside this one the switches like those, in addition to another circuit which is called the driver circuit, and the protection and everything in one chip. The only thing you need only to put your controller. So they reach to higher level of technology on those types, and they call it smart modules. if you would like to see those chip, can pass it to you. In addition to that, if you look at here, this one is a single phase DC to AC inverter. It's 200 watt rating, and if you look at this one, it has two optional. This is the input. You can get it for 12 volt input. 12 volt input. And the output, this is AC and output. You can get AC from here. So that means you can even take a power from your car battery, and then you can get AC. You can turn a TV with less than 200 watts. You can operate with that. You can operate this circuit. Okay. So look at here. If you look at that one, you see that this is the 4 transistor, those switches, in order to convert the DC to AC. And in this side here, there is I think a buck converter to convert the DC voltage from 12 to 5 volt for USB connection if you would like to charge a mobile or something like this. And also you can see the components of this one, and the signal, how to generate the signal and everything. You can see it's integrated inside that one in those chips. So everything is here, and it's one. And in addition to that, for the heat transfer for heat, so you can see that there is, for the cooling system, there is a fan here, right, to cool the components of this inverter. So that one. So, by the way, it has a filter, everything. If you see that there's capacitor with inductor and everything there to filter the harmonics components.
How can you control the output if you want it less than?
No, this is closed one. So if you would like to control an inverter like this, you need to buy either one inverter that can be controlled, like you can get like those from Texas Instrument, or you build your own inverter, of like the students or that one last year. So you have two options. But like this one, you will buy it from the market, it's closed, you cannot do it. If it is designed for 220, you will not have any choice to change it, unless they give you that option only. So, now, if we look at the circuit, this is the circuit for 3-phase. And how we can design the signal in order to convert this DC input to AC. The AC will appear from here, from these 3 points, A, B, C, okay? And these 3 it can be connected to a load like this one. So this one, that means this one connected to A, and B connected to B, and C connected to C, and this neutral connected to neutral. So if we design, actually, this one we can design, I can show you later, but it takes time a little bit if you would like to design, how exactly we design those. This is what is known 180 phase degree, which is used to convert the DC from AC. This is one of the technique, and to be honest, if you look at this one, every switch should operate with 180 degree, and then off for another 180 degree. This is one condition. Okay, and the second condition is, in each switch, each of those switches, it should operate only in each of this is one leg, right? And in each leg it has 2 switches, right? In each leg, one switch should operate only at one time. For example, Q1 should not be operated with Q4. Otherwise, you will create a short circuit. For example, if you operate this one, turn on this one and this one at the same time, you will get a short circuit, right? So this one, it should operate, the top one here, it should operate with this one, with these two, but not with this one. And the same thing, this one should be operated with this Q4 and Q2. And Q5 should be operated with this Q6 and Q4. So this is how we arrange those. But this design, this pattern, actually if you look at the sinusoidal waveform, you can obtain it from there. For example, let me show you one like those. PTs. So it would like to run that one. Let's see, VA, VB, VC. This is the output which is expected, right? After filtering, right? This is three phase, right? VA, VC. If I'm looking to those signal, I have the red one is VA, the blue one is BB, and we can change the color of VC to black in order to see it clearly. And we can change this one, the size of this one, and the size of this one, and the size of the third one. Right. Is it clear now? So look at VA, VB, and VC, right? So if I'm looking from this interval at just this 60 degree here, see that this interval from 0 to 60. If I look at to that one, I will see this one is related to VC. Okay, if I'm looking to this diagram here, VC in the top is connected to which switch? 5, right? From the top. And this red also in the top, right? From 0 to 60 in the positive side, right? So this red one is connected, VA, right? Is connected to which one? From the top side. From the top, connected to Q1. So that means from 0 to 60, I am sending two signals. One to Q1 and one to Q5. Q1 and Q5. Look at that one. From 0 to 60. Okay? Did you get it? 1 and 5. And it should be one switch from the bottom side, at least one on, while there is two from the top, one from the bottom leg in order to make one complete loop, right? So if I go to that one and look at my target, which is AC, the blue one, which is B, should be connected, should be on, right? So the blue one from the bottom leg is, which switch is that? Let's see. This is B, right? The blue phase, right? From the bottom connected to Q6, right? So therefore I designed my signal here to turn on switch 6. Did you get it now, Shabab? Did you get it?
Not yet.
Okay. You have, my target is to get sinusoidal like this, right? Right? And I need to turn those switches in order to reach to this sinusoidal, to mimic that one. Okay? So I will divide this one in 60 degree because I have 6 switches. Okay? So the first 60, this is the first 60, right? This interval. Look at this waveform and this waveform and this waveform only on this part. This one. Between 0 and 60.
Between 60 or
This is 60, right? 60. And the second 60 is that one, and so on. So this one here is 60. Okay, so this one from the top switch, and this one C, right? Connected to switch 5. Okay, and this one still in the top waveform, the top waveforms, which is here, should be connected to the top switches, and this one to the bottom switches. Okay, so this one and this one on this interval, this one and this one from the top. So two switches from the top, which is
1 and 5.
1 and 5, and from the bottom. From the bottom, no, 6. 6, if you look at this one, see here. The arrangement of the switches, it's odd in the top, 1, 3, 5. If you would like to remember how to arrange those. And then, if you subtract this one and with this one, you will get absolute 3, absolute 3, absolute 3. So you can get those numbers. Okay? So 1 and 5 with 6 in the first 6 degree. Let's go to next one. See here. In the next from 0 to 120, from here, from 60 to 120, this 60 degree. Still VA should be on, right? صح? And what's this? VB, which is, this is VC. So which switch connected to VC from the top? 5, right? So still, this one and this one on, and this one? No, and this one on from the bottom leg, right? Which is 6. In the next one here, after that, now, for example, if we look at this interval here, this part from that part here, this one VA on, okay, and now VB, which is switch 3 on, and from the bottom, switch which is connected to C. So it is connected to C. So this switch too. So this is how we can design those. So now we will get like those. So the first switch will be on for 120 and then off for 120. Okay? And now this one, we have seen it like this one, right? In those intervals, right? Now if we look at that one, the opposite of this one, 4, right? If this one on from 0 to 180, okay, this one should be off from 0 to 180, which is Q4. See? The opposite. Okay. And now this switch, the second one shifted with, this one should be shifted with 120, right? صح? It should be shifted with 120. So go to switch 3, you will find this is 60 plus 60, 120, right? And it will conduct for 180. Therefore, and this switch is opposite to that one. So this one will conduct from 120, okay, till 120 plus 180, right? To this point. So you will find that when this switch is off at that time, where's that? See? Was off, and the left other side is on, right? And you can continue for the next 2. Is it clear? So this is how it can be generated. Now, if we suppose that I generated those, if I would like to analyze the voltage of those, suppose that at the first interval, Q1 is on, Q5 is on, and Q6 is on, just for the first interval. Can you tell me what is the voltage ABC on that one? This is how we, can you think how we can get those? Can you draw a circuit here? Let's draw that one. in the first interval from 0 to 60 degree, right? You can see that Q1 from the top leg and Q5 are on, right? And from the bottom leg, Q6 is on, right? On. Now, if I draw that circuit, okay, so Q1 is on, so that means this one is on and it goes to A, right? Okay. And Q5 is on and it go to point C. And from the bottom, from this side here, this one is on and it is connected to B. Now, this is the three-phase, right? B is connected to this point, right? Okay, this is point B. So there is a load here or resistance here. I'm assuming now all of them balanced. And then the neutral in the middle, which is this point. Now, from this point, one load goes to C and one load goes to A, right? So, from this point, which is the neutral, one goes to A and one goes to C. This is how it looks like from the circuit analysis. Now, if you look at this circuit, if I assume this one, let's say this one, let's call it now resistance, and let's call this one R, R1, R2, R3, and all of them equal. So we call them all of them R. Let's assume them equal. Okay. Can you tell me what's the voltage across between A and this is N, right? A N. What's the value of this voltage? If I assume this one Vs. Can we look at the circuit? So your circuit will look like this if you would like to just make it clear. Just take it like that. And then to this. And then all of them equal value. Vs. So this is this C and A, it's same node, right? So this is A or A or C, right? Both of them they are in the same point. And this one N and this one B. Can you tell me AN? What's the value of AN? This is those two in parallel, right? So R1 by R2 over, that means it's R over, the total of this one R over 2, right? And this one R. So the total of the resistance is, this is 0.5 R, which is R over 2, plus R. So the total is 1.5 R. So R total, 1.5 R, right? Now, if I would like to get the voltage here, okay, what's the voltage?
0.5 over 1.5.
Yeah, but this is the total of this 1.5. So if I use voltage divider rule, I will get that one here. So VAN equal VS multiplied by 0.5 R over 1.5. The total is 1.5 R, right? Is it correct? So now what's the value of this 1.5 over 1.5? Yeah, 2 over 3, right? So 1 over 3, so 0.333. So VS is 0.33 of BR. So that means I will get the output during this interval, that one only, the small one, that one, I will get Vs equal third of this value. So if I go to that, then I got that one here. VANC, it's 1/3 of this value. That one, 1/3. And then if I go to the next interval, you can continue. You can continue and you can get with the same circuit like this one. Okay, you will get, if you try to apply this one, you will get VAN, which is 2/3 and so on. So you will get like 6 pulses the output like this. You can apply for each interval a circuit like those in order to get the value of that voltage. Did you get it, Shabab? So now we can get VAN, VBN, VN. Also we have also line-to-line voltages, right? So we can get, for example, VAB, VBC, and so on. We can apply those circuits. For example, if I ask you on this interval, can you tell me what is the value of VAC in this case, in this first interval? What is VAC? The volt. It's same node. So the value of the voltage is 0. So if you go to this, the analysis here for VAC, right? So this is 0, VCA, right? 0, right? And if I ask you what is VAB from A to B, A to B. VS, exactly. So VAB during that, so you see it's VS, and so on. So now you can get those. What is known in this case, this is, if we do it like this one, it is known like 6-pulse inverter. They use it in BDO for Fourier production. The same technique, and they have the same type of controls to get those. So this is how they do it. So if we go and simulate like that one, six pulse like this. This is, I'm trying to do like what we explained now. For example, for the first switch, which is this one, I will turn it on for a while, and then I will do, see here, I will turn it from one peak and then keep it on for 50 due to cycle of 0.5. So that means I have 50 hertz and I keep it on for the first half cycle, right? And then turn it off. And then and the opposite for this one. So I'm using here the NOT gate. You see that NOT gate? So if this one is on, this one should be off. And the same thing, I will shift these two with 120. I will turn on this one and I will close that one with the NOT gate. And the opposite, if this one on, the other one is off. You see? That's why I'm using this NOT gate. So if I run this one, cancel that one first. I can see if I have, this is V, for example, if I would like to see VAN, I would see it like 6-step like that one, like this output, which is here, like that one. So from this DC, I got this signal. You see? I got, if you see, it's just a 6 steps, but it's AC, not DC now, right? It's AC. Yeah, exactly. So this AC, if I add a filter, I can get rid of those ripples, and then I will get a pure sinusoidal. We cannot say exactly pure, but at least we will try to reduce the harmonics or mitigate the harmonics in order to get it nearly pure sinusoidal waveform. So if we just would like to plot we can plot the 6. We can also plot line to line if you would like to see line to line. We can move this one, for example, to phase here, to phase B, and we can see the line to line. See here, this is what exactly VAB, which is like this one. So you can get the line to line value of the voltage. See here, exactly mimic like that one, right? Exactly same as that one, right? Now, so in this case, what we have seen now, if I have a DC, that means I can get an AC, and I can get this AC with different frequency. I can make this DC to give me, for example, 50 Hertz in the output. I can make it 60 Hertz. I can make it 120, whatever I like. While I'm not exceeding the limit of those, I can get different frequencies from that. So I can operate, so I can change my frequency. And if you know that, for example, induction motor, if you would like to change the speed, one of the techniques to control the speed, you can change the frequency, right? If you can remember the relation of, for the induction machine, F equal 1 to 1, sorry, N equal 1 to 20 F over B. This is the synchronous speed, and this rotor speed, it should be split with some lower value, right? In order to operate an induction motor in stable region or characteristic. So that means if I change the frequency, I can get different speeds, right? So I can speed up the motor, I can decrease the speed. Also, if we would like to control, for example, we can also suggest another type of controller. We can change the frequency, or we can change the value of the voltage, or change the sequence, or change the voltage and frequency. And we can do it also with those. We can change the frequency. We can by changing the time or the period of each steps, right, of the period. Also, we can get variable voltage and variable frequency, another method, by using this pulse width modulation. Yesterday we have seen in the DC to DC also pulse width modulation, right? But at that time was our reference value is fixed, which is DC, one straight line, right? And change that one if you can remember. But today we can keep this triangle waveforms, which is the carrier, and I just use a reference like this one, a sinusoidal waveform, and connect those two to a converter, for example, the same as we have done yesterday, and compare. For example, in this interval, this small interval, which one is higher, the carrier or the reference? The reference, that means the switch which is connected to this, the switch was connected to this signal, it will turn on the top switch and turn off, for example, the bottom switch. Okay. In the second one, now it changed, right? So now the carrier is higher and the reference is lower. So that means the top switch will be off and the bottom switch will be on, and so on. Now, if you would like to increase the value, you can change the ratio between this one, the reference, and the carrier. So you can make this one with lower peak, you can go down. So that means you decrease the duty ratio, or you can increase the duty ratio up to here, which is known as 1 with the duty ratio, or the modulation index, which is known. And in this region, if you're trying to change this one from the reference from 0 till here, it is known a linear changes. So if you exceed this one, it will be known as over modulation index. If you would like to ask me about this one, I can explain it after the lecture, or you can come to my office. I will be happy to explain exactly the details of those, because we don't have enough time now to discuss those and how we can get those. Now, this is how we do this and how we can. Now, for example, if we connect this one to switch 1 and switch 4, I will bring another signal like this one and shift it with 120 and connect it to this switch, and with NOT gate to this switch. Is it okay? And another with 240, shifted with 240 and connected this one and the NOT gate to that one. Based on that, I can get an output of the AC with sinusoidal, but also it has harmonics. If I add a filter, I can filter those. And if you would like so you can, if here, for example, if V reference higher than carrier, this is the statement how to turn on and turn off. We discuss it now. This is the operation, for example. If you look at VAO, this is on because this one is higher than the reference signal, but for the other one it is on when it is on, because the blue one, which is the carrier high, which is the reference higher than the carrier signal, right? Therefore it's on for this PO, and so on. And we can analyze those. So let me show you an example. This is the modulation index, which is V reference over V carrier. Let me show you this one in an example, better to simulate. This is the pulse width modulation. This is how I create those pulse width modulation. I will create an AC signals as a reference, and then compare them with a triangle signal, and then add them to a comparator to compare between them, either on and off, which is 1 and 0, and then connect those output from those one directly to the, for example, to the top switch, and for the bottom switch add NOT gate to make the opposite. When the top is on, the bottom should be off, and so on. So this is how we do it. So if we run that one, let's close those first. So nearest one located, look at how far, it's with high frequency. So designing a filter for pulse width modulation will be smaller than designing a filter for square wave type of inverter. But and the beauty of this one as well, you can control the value of the voltage by changing the pulse width the modulation index. Okay, and you can change the frequency. You can, so it has good opportunity to use it to change the voltage, the frequency, the phase shift, whatever you like, for the drive. And also for the, if you would like to connect this one to the grid, it's easier to design a smaller filter to compare to the 6 pulse. But you might ask me, why VDOD while while 6 pulse has that harmonics? Why they don't use that pulse width modulation with higher so they can design small filter? This one also, it has in the drive, it has another problem which is known as reflected wave. It can cause a reflected wave, and it might damage even the inverter itself. If it is connected, for example, for long cable like in the well for oil production. But the other one, because it has only 6 pulse on it, a reflected wave will not appear that much compared to that one. That's why they prefer to go to 6 pulse than to go to that type of inverters. So let me show you the operation of this one in this MATLAB simulation. This one will show you exactly how it works. You will see this is a battery here, and this here IGBT average, you can assume it like what you have now. It has 6 switches like that one. Like that. So there is, you can assume 6 switches inside that one. And then those output pins, so this is input pins, and this is VA, VB, VC, and this is the gating where we should send the signals. And here you need to send 6 signals, right, through that switch. So this one will generate 6 signals to each switch in order to turn it off and turn it on. Okay? So exactly, this is the pulse width modulation generator. Here it generates directly the pulse volume. And I can get I can supply this load with AC. So let's simulate this one and see. This is my input. If you look at this one, it's 780, right? 780 volt. Now, and if I look at to this, the modulation index here 0.6. Okay, and the frequency of the reference is 50 hertz. And the frequency of the carrier, see this is the carrier, right? Now it's made in a block, right? The carrier 22 kilohertz, your frequency reference is 50 hertz, and the modulation index 0.6. Means that like this. The ratio between this one here, the peak, or between this peak of that one and the peak of the reference and the peak of the carrier, this one over that carrier, it's equal 0.6. Is it okay if you divide that one using this equation? V reference over V carrier, you get 0.6. This is what we meant here on that modulation index. So this one will generate those triangle waveform internally inside and compare it and put the comparator and include the switches. So now the switches will be sent to that one in order to turn on and turn off, like this process. So those whole process can be integrated or can be equalized to this box here, which is pulse generator, to create 10 pulses, 6 pulses. So let's run that and we'll see the output. Now it's run. See, this is the DC, and this is the output before the filter. So this is our filter, right? And this is the output before the filter. So if we look at that one, this is before the filter, like what we have seen on this one. The same thing, right? The same as this one, which is in BSIM. This is, you can see it here. Now, I have this signal, right? I need to filter it in order to get an AC like this. Okay? Therefore, I will pass this one through the filter. So this is my filter. And this filter, it's LC filter, which is low pass filter. Look at here, it consists of inductor and C, capacitor. So when you connect this one, okay, the filter, okay, you have seen yesterday it's absorbed the noise, right? So those harmonics will be absorbed by this filter, see? It's there. And you left with this output. Sorry. Oh, it seems that I closed everything, so let me turn it on. See? I have input DC 780. I change it to this AC. This is before the filter. And then add it to filter, I can see the output, which is sinusoidal. And this one, it's blocked the whole the three phase, from A, B, and C. Therefore, I can get from 70 to this value of voltage. Now, I can increase the voltage of this one. Now, look at the peak of this one, around 250, right? If I make this one, for example, I make the duty cycle, sorry, the modulation index, for example, 0.8, you will see that, or 0.9, you see that output voltage will increase. Let's run it now. See now? See the peaks, it goes above 300, right? Near 400, right? So that means I can control the value of the voltage.
But still there is noise.
Yes, definitely. It will be, there is noise, because the filter, you need to smooth it, you need to increase the filter size. Yeah. Or it depends also on the load. For example, if you design like what you have seen in the first video, if you change the load, the ribbons appear again, right? The same thing. You have LC filter. You can block the transfer function of all the resistance, which is the load, and the LC filter, and see the transfer function between this input and the output, and you will determine that what the filter will do. I will show you in the project which the student, they have done it last year now. So let's see it through, let's go through that project. So this is the team of the student who did that project. And this is how they designed the project. They made their methodology. They gather the information, they study, they make like literature survey about three-phase inverters, and then they started to design and simulate. And then after that, they started to evaluate the results. If the simulation is okay, they went, and after that, they went and implemented in the lab, and then evaluated experimentally. This is what they did. They process like this: start literature, read about the inverters, how it makes, and then once they know that one, they design it by simulation. Like MATLAB and VSim, they implemented. After that, they test it and see the results. After that, once they finish this step, they went to the lab and they buy the components, and they got the components and assemble it in one breadboard in order to do it experimentally. And this is what they did exactly. This is the simulation. They simulate the inverter as an isolated. They add a control loop. I am happy to explain to you this control loop later if you want. I don't mind. You can come to my office and it will explain you everything here. And also they connect that one to the grid. So they do this one, they make it with VF control, voltage and frequency control. And that one, they make it with B and Q control, and actually they operate this inverter as unity power factor. And then after that, after that, they start to design the. After that, what they do exactly? They test the components and then they try to collect the component like the data acquisition card to make their controllers, LC filters. They design that one. Also, they bring or they bought the IGB transistor, assemble them all together in one component, and then evaluate it like those flow chart. So this is some components they added here. You can see this is their components: transistors, switches, L, and also the inductor and the capacitors. This is the data acquisition card from Texas Instrument. And then they made a drive circuit to turn on and turn off the switches, because you cannot connect directly this data acquisition card to the transistor to turn it on and turn it off. You cannot, because the value of the signal which is generated is too low. What they do, they amplify that one by making those gate drive circuits. That one, another drive circuit to amplify the signal in order to use it to turn on the main switches. So this is the signal which they got it after the drive signal here from this side. Now this is amplified. See, this one before the gate drive up, and this is amplified after the gate drive up. Okay? And after that, they made their own inverter. This is single phase. They started with the single phase. This is the, and then they implement the three phase. See now, 6 switches, six transistors, right? And then they add their filters. This is the filter, and this is the load, the resistance. And they was able to get 3 phase. You can see here 2 phase, because the oscilloscope, we don't have in the lab oscilloscope that measure 3 at the same time. So they measure 2 and then they check the other one. So this is the whole component. You can see they made, this is the drive circuit which is used to turn on this transistors, and then the output from here, it's not purely sinusoidal wave. They add that filter and then connect it to the load, as you can see it here. And then they test this one. How to design the filter? This is how they designed the filter. They, as I said, they implemented the transfer function of the LC and the load, and they blocked the board plot, and they checked that they need that to pass the frequency which is lower that point. So the frequency which is here, it will pass, and any frequency higher than that point, it will be attenuated or eliminated, right? And this is their design. They make it 2 millihenry, and the capacitor is 47 in order to do like that. So this is the output before the filter. And you see that it has lots of harmonics component, and they are planning to filter those by the filter. So this is they would like to pass this sinusoidal waveform here and cut this noise. You see it's 98. Now after the filter, you see there is some noise still, but they were able to filter the noise. See now? Only this is what it does. But you see makes that smaller. But you have seen they filter all the noise, and then just like the main component. And the THD is 2.48. It was 98, and look at how much. This is the total harmonic distortion to measure how is the harmonics of it. It's as index. This is 3 phase output. The whole 3 phase. You can see this is the phase A and phase B and phase C before the filter, and this is after the filter, as I showed to you on the video, or in in the simulation. So THD is less than the standard of IEEE, which is less than 5% for low value of voltage. And when they connect it to the grid, they're able to get 2.93 total harmonics distortion. You can see now, and they were able to send the power or to inject power to the grid. You can see that they injected those power, which is about 10 kilowatt, right? And the reactive power it's 0, right? So that means they operate their inverter and unity power factor, and they were able to inject real power